Hi friends, welcome to GMK tutorials. In this video, we are going to see about the power gating control. So, up to now, we discussed in 5th unit, that is nothing but leakage power minimization concepts. We discussed what is meant by what is the necessity of leakage power. And the second video, how to design different threshold voltages, that is also called as a multiple threshold voltage fabrication techniques. And we discussed about the DTCMOS, MTCMOS approaches, how it is very helpful for the reducing the leakage power concept point of view. And coming to the power gating management. So in that video we discussed different types of what is meant by power gating, what is the difference between power gating and clock gating, how it is efficient, power gating is efficient compared to the clock gating, and what are the topologies of a power gating, these kind of the isolation strategies, state retention strategies. These kind of the topics is already covered in the previous video. So up to now, those people who are not subscribed our channel, please subscribe our channel. Okay, thank you. Okay, let's move on. So power gating control. So generally, suppose if you are taking any system, suppose let us consider any system, whatever it may be. Suppose if you are taking any system, let it be considered as a one circuit. So this is a power gating block. Okay, this is a power gating block. You are providing a power supply to this subsystem. It is a subsystem. Okay, suppose if you are providing a power to the subsystem, to the power gating concept, the basic agenda is nothing but whatever the voltage you are supplied to the subsystem, you are not provide the power rail or direct supply to the subsystem without on the corresponding subsystem. That means without settle down the corresponding subsystem condition, you are not applying any kind of the supply voltage to the subsystem. So obviously there is some question mark is arised in each and every student mind. Sir, what happens if you are applying the power supply without enable the corresponding device to the complete static mode? At that time what happens is nothing but, suppose whenever we are switch on the any switches in our home appliances also, certain times we are performing multiple switches at a time, just we are pressing very fastly. At that time there is some sparks will be generated on the corresponding boxes, it may be extension boxes or anything. So for that purpose you have to on the power supply very slowly. That is the minimum criteria you have to follow whenever you are providing power supply to the any device. That is the basic necessary. So from this basic point we have to analyze the what is the condition, what is the how to control the power gating. So how this power gating concept is useful to supply this. So the basic power gating means that here power gating means that which produces the power to the subsystem. That's why we can call it the power gating. That means the circuit is act as a one kind of the switch. This switch is used to provide a power source to the corresponding subsystem whenever this power gating concept is enabled or whenever it is a true condition. So then only it is possible. Okay, so that is a basic agenda. As well as if you are switching on the corresponding power supply at a time, what happens is that the maximum current is drawn from the battery at a particular instant. So that instant is generally called the instantaneous current. This is nothing but instantaneous current. So this current is nothing but surge current. We can also call it the inrush current. Okay, inrush current is nothing but it is a maximum current drawn from the power supply. What happens if the maximum current is drawn from the power supply? You know guys, if you are drawn the maximum current from the battery, means that the life of the battery life of the device is also decreases. That means the corresponding device battery lifetime is decreases. So that is also one of the major drawback. Moreover, we are using handheld battery devices nowadays. Most of the chips are operating with handheld batteries only. If the battery life is decreases, means that obviously that function of the device is only limited to certain extent only. So that is also one of the limitation, right? So this current is generally called as inrush current or insurge current. So what happens if the insurge current is produced in the corresponding system? What is the basic necessity? So here one more intention is nothing but if the inrush current is increases, is maximum, it is also affects the register present in the corresponding device or maybe other devices continuously on condition. Suppose if the subsystem is there, so if you are providing such a time, there may be another subsystem is also like this. So in this subsystem also some registers is there. If you are providing such a kind of inrush current, obviously it is affected this resistor functionality as well also. Okay, so that is also one important point. Okay, let's move on to the topic. So inrush current limit the current when the power block is switched on. So an excessive inrush current is also causes the voltage spikes on the supply. Okay, it is also causes the corrupting the resistors in the always on block as well as retention resistors in the power gate also. That is already we discussed. So for that purpose we have to follow the one daisy chain method is the one technique. With the help of a daisy chain method, what happens is that this daisy chain method is delays the corresponding power signal to the certain extent up to the corresponding device is going to be in on condition. That is the basic principle of the daisy chain. So it result of the daisy chain, it takes some time from the assertion of the power up signal until the power up until the block is powered on. So that is the basic. Suppose if you want to performing more functionality to this one, we can the more aggressive approach is nothing but turning the corresponding switches with several power up control signals. So we don't have any limit that one. If you are designing such a corresponding circuit in a particular fashion, we can achieve the corresponding power up sequence with some proper designing. Okay, so that is a very important. So this is nothing but a very brief introduction. Okay, let's move on to the next slide. So this is a activity profile with a realistic power gating. So here our basic intention is nothing but you have to provide the corresponding power supply, right? So here previously we are using the power gating signal is like this only. Just this is a power signal in the linear condition, it's active condition. So this is a scenario. This is nothing but a leakage power. Okay, but what happens if you are the current is suddenly drive like this, there is a possibility of spikes will be generated. So for that purpose the current is linearly increases, therefore no spikes will be produced in the corresponding circuit. So for that purpose the power gating can be provided in this fashion only. So in the ramp wise fashion, so no spikes will be produced in the corresponding signal. This is nothing but activity 1. In the when the device is in active condition, obviously two types of power dissipations will be takes place. One is nothing but dynamic, second one is nothing but leakage power. In the standby mode, we can also call it the sleep mode. What happens is that the only leakage current is responsible for the corresponding power dissipation. So that's why it is a scenario. So this is a power gating control without retention. Without retention means that we are not saving any kind of the data in the corresponding registers. That is nothing but that is the meaning of retention. Retention means that save the data in the registers. Okay, that is the basic criteria, right? So here this is a clock signal. This clock signal is used to enable the which duration you are going to apply the power gating to the corresponding block. So first of all you have to isolate the signal. Isolation means that just you have to separate the corresponding device from the all other activated signal. After that you have to apply the reset signal, just the reset, then you have to apply the power up block. So generally this application or enable, generally we can call it the enable signal. Technically we can also call it enable signal, is also called assert, A-S-S-E-R-T. So assert the signal. Okay. So that is the control flow can be discussed in the next slide. So this is a procedure. Just first assert the isolation control signal, assert the reset block, assert the power gating control signal to the power down block. At the same time, if you are going to performing the reverse disabling purposes also, first of all at the time of a switching on, the same signals are sent in a reverse order as follows. So last signal is nothing but what is the last signal in the previous slide? So that is nothing but power on button. It is a quite reverse operation, right? So this is a follow in this method. First power signal, reset signal, then isolate signal and clock signal. This is the scenario. So just you have to follow the same fashion here also. So first one is nothing but deassert the first is nothing but deassert the power gating signal and deassert the reset signal. then deassert the isolation control signal to restore all the outputs, as well as restart the clock signal without glitches and without violating the minimum pulse width mean. So what is the meaning of this one means, sir? Suppose if you are applying the clock signal with some on-off time is nothing but like this. Whenever you are re-enable or whenever deassert the clock signal, the same time period and same amplitude is also maintained within the clock signal. Why? Because if the corresponding on time and off time is changes, obviously it is also affects on the performance also. Because of this on off is also very important. So we can also call this we can generally, in case of a stable multiple, we can also call it on time plus half time is generally called as a duty cycle. So the duty cycle is also very important in case of the power gating circuit. So based on that one, we can control the mechanism of the on off time of the processors also certain situations. Okay. Next, move on to the next one. Suppose if you want to save the data present in the corresponding register, this is a scenario. So just to before reset the corresponding before asserting the reset signal, just you have to apply the one save signal as well as one restore signal in the last one. Okay, so that is the procedure for this one. Okay. So just enable the clock signal, initially assert the clock signal and isolate signal. Then you have to, before reset the corresponding data, just one save signal is enabled. That is nothing but assert the save signal. Assert means that enabling, or enable is both are same meaning. Okay. Whenever you applying the save signal, that saves the data, whatever the data present in the corresponding block. Okay. As well as after that you have to enable the reset clock signal, reset signal, then power on signal and restore signal. This restore signal is nothing but reverse operation. If you want to go for the reverse operation, means just whatever the data stored in the register, that can be take the back and power on the corresponding signal and the reset option, then followed by the save signal and followed by the isolation signal and clock signal. Here no clock signal, only clock signal is only save signal is in the first cycle in this direction. No save signal will be disabled, because after that only the signal is disabling, right? So that is so here the data is stored in somewhere else. So that's why we are using the save and restore signal. So that's why it is called a retention strategy. That means power gating control with retention. That is the basic difference between previous one and this one. Coming to the next one. So this is the procedure reverse operation means that, but same at the time of switching on the same signals and the same reversed. So power gating off condition, on condition. So deassert the power gating control signal, deassert the reset, ensure the clean initialization, assert the retention condition, isolate the control signal to restore all the output and reset the clock signal without any glitches, and follow the minimum criteria, that is nothing but on off time as well as on time and off time. We can also call it a duty cycle, which maintains, that is a very important criteria. That means why it is important. If you know guys, if the clock frequency is also changes, that is also affects the performance of the system. I think you guys remember that if the clock frequency is increases, obviously the power dissipation is also increases. So for that purpose, you have to maintain the same on time and off time of the corresponding clock is also very important, right? Next one, power management. What is meant by basically power management? Generally, the power management means some of the devices in the circuit may not be used. Still, the complete operation is going to be performed. So at that time, you have to identify such a kind of the devices. What devices are in the ideal condition? You have to switch off the power supply to the particular devices. Therefore, obviously, we can save the power, as well as if you are not applying any kind of the power to the particular source, means that no static power dissipation will be takes place, right? That is the basic criteria, right? Whenever the device is in on condition, then only static power dissipation will be takes place. Suppose if you are not providing any kind of the power to the particular component, means that no, there is no chance of power dissipation in case of the static mode, or we can also call it the sleep mode, we can also call it the low power mode. So that is the basic idea behind the power management. So that can be discussed in this. So this is a complete discussion of the corresponding related information. Just we will take some process as an example. Okay. So approach is used to execute process to regulate the power consumption. So as well as the on time and off time of the corresponding processor is also saves a lot of power in terms of a dynamic power saving as well as in terms of static power saving. Okay. Next we will move on to the next slide. So this is a linear power savings of the conventional method. Generally, suppose this is nothing but power. So this is this in the y-axis represents the power. It is nothing but activity. Activity level means the corresponding condition of the device. When it is an active condition, what happens is that when the activity level is 50%, at the time you have to on the corresponding power signal. If the activity level is very low, at that time you have to apply half time. That means when the circuit is on condition, you have to apply the power to the corresponding device with the low power. What happens if the low power means that suppose if you are applying low voltage to the corresponding device means that obviously with a minimum power, that means if you are reducing the supply voltage means that obviously power dissipation is also reduces. Power dissipation is also reduces. So for that purpose, based on the activity level, you have to apply the corresponding power to the device. So this is a traditional power management. It is the activity level, normal level. Activity level is 0.5. Therefore 50% duty cycle. That means you have to on the corresponding power only particular period only, not complete cycle. So that is also very important, on time and off time. Okay. Next, move on to the next slide. Combining DVFS and power management. So what is the necessity of the DVFS in case of the power management? So power management means just you have to set up the corresponding power supply to the devices which are not used in the corresponding circuit, right? So at that time, this is very helpful. Obviously, this is a very important concept actually. So this is nothing but combining DVFS and power management. So however, the DVFS ranges, it's generally suppose let us move to the next slide. So I will explain here. So generally suppose let us consider in this scenario. So generally DVFS means that one of the DVFS is nothing but dynamic voltage and frequency scaling is useful for maintaining the performance as well as the power dissipation. But some of the devices, suppose up to 0.25 it is possible to reduce the power supply. Beyond that one, it is not possible to reduce the power dissipation. Why? Because the 0.25 is the minimum voltage you have to apply to the particular device. If you are still reducing the voltage beyond 0.2 volts means the device cannot perform the normal operation. So that is the drawback actually. Suppose if you are performing the traditional power management, this is the situation. If you are applying the power gating, power management, this power dissipation can be reduced like this. Suppose if you are applying the power management, suppose if you are applying the DVFS, this is the situation. So up to this only DVFS will perform. Beyond that one, it is not possible to reduce the power dissipation like this. Why? Because this point is the only minimum point you have to reduce the corresponding supply voltage. If you are still reducing the supply voltage beyond this one, the corresponding devices cannot perform the normal functionality. So for that purpose, if you are using both the concept power management as well as DVFS, we can reduce the power dissipation very efficiently by judiciously combining the power gating concept with DVFS. We can achieve the low power dissipation. That is the basic idea. So how it is helpful? Suppose up to this point DVFS is very helpful. That means DVFS, dynamic voltage and frequency scaling, is efficient for reducing the power dissipation. But whenever you are reaching the minimum supply voltage, after that you have to apply the power management. The power management basic criteria is nothing but you have to on the corresponding power, you have to power on the corresponding device. You have to power on the corresponding device whenever the activity is very high. If activity is no activity, activity level is very less, just you have to shut off the corresponding power. That is the basic criteria. Therefore, whenever we are not providing the powers to the corresponding device in the half condition, obviously it reduces the power dissipation. Okay, so that is the basic idea of the power management and DVFS. The basic idea DVFS is not possible to always to reduce the supply voltage to the very lowest value because of some of the CPUs and other devices is operated with a certain critical minimum voltage. If you are still reducing the minimum voltage beyond the minimum voltage, it is not perform the normal functionality. So that is a drawback. So for that purpose, the power gating used, where the power gating is also efficiently used. Power gating basic concept is nothing but we can switch on the power to the particular device when the activity is performed. If it is not performing any activity, at that time you have to power off the device. Therefore, that is the basic criteria. If you are combining those two techniques, we can achieve the DVFS with the conventional management. So that is the basic criteria, right? Next, we will move on to the next one. So dual VT assignment approach. It is also one of the most important concept. It is also called as a dual VT assignment. We can also call it a DTCMOS. The availability of two or more threshold voltages on the same chip is open up for the new opportunity of making up the trade-off between the power and delay. Okay. So as well as, unlike in case of the MTCMOS, is also additional sweep transistors are used for MTCMOS. That means in case of MTCMOS, we are adding two transistors as well as one pull-up and one pull-down. That is also increasing the size of the device. That is also one of the drawback, right? So this is not only avoids the additional area, as well as delay is also one more parameter is added in case of the MTCMOS. So in order to overcome such a kind of the problems, we will go for the DTCMOS concept. It is an extension for the multi-level threshold voltage. That is also called as a MTCMOS. Okay. Next, we are move on to the next slide. So the delay of the logic gate is increases with the threshold voltage. Generally, we know that guys, delay of the logic gate is increases with the threshold voltages. Okay. So because why? Because delay is directly proportional to VDD into by 1 VDD minus VT. So that means VT is also plays a very important role in that, as well as the static power is also due to the leakage currents in the corresponding device. As well as, suppose if you want to reduce the leakage current in the corresponding device, obviously what is the another alternative? You have to increase the high threshold voltage. Whenever if you are increasing the high threshold voltage, leakage current is decreases. As well as if you want to maintain the better performance, obviously you have to reduce the low threshold. You have to maintain the low threshold. So that means high threshold voltage is the circuit is the one can try to realize the digital circuits with the speed corresponding to the low VT transistors. So that is nothing but basic criteria. Low VT transistors as well as high VT transistors are responsible for maintaining the performance as well as power dissipation. That's why these are the two important parameters you have to keep always in our mind, right? Next, we will move on to the next one that can be discussed in this slide. What is the importance of the low VT and high VT? So this is also same scenario. We can designing how it is very helpful. The first circuit is designed for a high performance application by optimizing the dissipation with a constant delay and with a compromise in terms of the performance. Okay. So that is a basic concept, how it is very helpful. So this is the overall explanation regarding the DTCMOS. So I will explain with the circuit actually. So here the basic agenda in this case is nothing but this is a circuit diagram. Just suppose if you are taking any, so this is a situation. So this is a circuit actually. Suppose if you are applying in case of the DTCMOS, so this black color gates means that this is generally called a critical path gates. So you have to apply the low threshold voltage, low VT to the critical path gates. Why? In case of the critical path, is nothing but it is the shortest path to reach to the output. Suppose if you are applying the high VT transistors to the critical path gate, means that obviously delay increases. So that is the one drawback actually. So the critical path delay is always very less. Then only we can attain the high speed. So that's why it is very important. So that is the first consideration. Okay. So first of all, so second thing is nothing. So darker gates on the critical. So high VT is assigned to all gates in the critical power. So in this case, Initially this here the light color gates, no shaded color is nothing but non-critical path. So in this second diagram, this is nothing but this can be represented as some shaded color. It is also called as a gray color. So this gray color means that all gates are assigned with the high VT transistors, and dark color gates are assigned with the low VT transistors. Okay, so that is nothing but 0.25 is a consideration. So B diagram third C is nothing but high VT with 0 point assigned to some of the gates in the critical path. So in case of the third one, third consideration, so it is nothing but a, so in this diagram also critical path gates are also assigned with low VT, as well as some of the gates in the critical path is also assigned by the high VT transistors. High VT. Why? Because we have to reduce the leakage current is also very important. Okay. So only some of the gates is assigned with some leakage current is also as well as. So next one. So last consideration, high VT 0.46 to some of the gates in the critical path. So 0.460, that means in each and every case we are increasingly 0.25. So obviously each and every one is having down. Sir, why you are taking always is this leakage current is also. So why? Because generally the nominal range of threshold voltage is 0.2 of VDD to 0.5 of VDD. So for that purpose, beyond 0.2 it can be treated as a high VT. That's why we are increasing the threshold voltage from 0.25, 0.35, 0.45 like this up to 0.5. We are assigning the different threshold voltage to the non-critical path gates. Okay, that is the basic agenda. Okay, so this is just a dual VT CMOS circuit diagram. So these are the critical path. This circuit represents the critical path. This line is a critical path direction. This is also okay. So this some of the gates with white represent, that is also non-critical path that can be assigned with the high VT transistor. Okay, so this is a overall discussion about the dual VT. So this important point is already mentioned here. Okay, please go through this one. Just the availability, I will explain. It is a very important question. The availability of two or more threshold voltages on the same chip has opened up a new opportunity of making up a power and delay. So that is very important. Unlike empty CMOS approach, where additional sweep transistors are used to reduce the leakage power in the standby mode. Therefore, two or more threshold voltages may be assigned to the transistor, realizing the functional gates in the circuit. So in case of empty CMOS circuits also, we observe that two transistors are added in case of the originality of the circuit. That increases the this is not only avoids the additional area and a delay due to the instead of sleeping transistor, but power reduction takes place in both standby and active mode of the transistor. So the DTCMOS is overcomes the limitations in case of the empty CMOS. So for that purpose, we are prefer low VT transistors as well as a high VT transistors. The key idea is use a low VT transistors for realizing a gates on a critical path. So there is no degradation in the performance. As well as you have to maintain the high transistors in case of the non-critical. Therefore, you can reduce the leakage current. That is the basic important. The leakage current, how you are using the threshold voltage in case of the any circuit is very important. Always you have to remember 2 points. Low threshold voltage is used to maintaining the performance. High threshold voltage is used to reduce the leakage current. That is very important, guys. You have to always keep this point is in your mind. Depending on the application of for which circuit is designed, there is a two alternative approach: delay constraint and energy constraint. The first consideration is nothing but circuit is designed for high performance applications by obtaining the power dissipation with the constraint delay. That means this designing of the circuit is two factors. Generally, some of the circuits may be very necessary for a high speed application, but power dissipation may not be consideration. Maybe certain conditions, power dissipation is maybe very important. Speed is not a criteria. So at that time, you have to go for the two approaches. The basic idea in this case, realize the circuits in low VT transistors therefore in the critical path, and high VT transistors on the non-critical path, therefore you can achieve the highest performance, because of low VT means that it increases the performance. Okay. And the second thing is nothing but, in the second case, the critical the circuit is designed for battery operated handheld batteries, where the energy requirement for the circuit is minimum at the expense. That means speed is not a criteria. So for that purpose, based on the observation that small compromise in the performance, therefore you have to assign the assign the high VT transistor reduction. So that is nothing but so this is dual VT CMOS. They may be termed as energy consumed. So we can assign the high VT transistor. So in both cases, the key issue is how efficiently two threshold voltages are assigned to the MOS transistor. That is the final important thing. Okay, so that's why it is a very important consideration, guys. You have to keep always this, remember these 2 points. Highest threshold voltage means, just I will explain here also, with some low VT transistors. This is the conclusion for the 5th unit also. So these are the two important low VT transistors. Low VT is used for increasing the speed. So if it is increasing the speed means it can be achieved by decreasing the delay. This is also very important point. Second thing, high VT transistors. High VT transistors means that obviously increases the delay. As the delay increases, speed is decreases. As well as this high VT transistors also reduces the leakage current. These are the two important points always you have to keep in our mind. Okay, this is also very important, guys. Okay, so as well as in the one more important point is nothing but, basically this is a general consideration. Suppose if you want to go for the circuit point of view, you have to use VTH hopping. VTH hopping means it is also one kind of the circuit which is used to shift the low VT and high VT the values with the help of a circuit that is generally called as a frequency VTH hopping. That is a one more circuit in the leakage power minimization concept. Okay, so thank you for watching GMK. Thank you each and everyone who supported me directly or indirectly. Thank you. Thanks.